Good evening, everyone. So I'm Farah. I'm currently doing my PhD with Imperial. I just started in January. So today I'll be sharing the introduction, basically, of what my PhD is about. So the title for this evening would be the application of multi-criteria decision analysis and geographical information system in CCS. Before I start, I just want to do a bit of a recap about the EAGE CO2 storage masterclass that I had the opportunity to attend in March. This masterclass was a very good opportunity for me. I just started my PhD, and there were all these experts in one room throughout the week sharing about a whole CO2 storage project design and optimization. I'm sure most of the people who have been working in CCS know Philip Ringrose. There was Martin Lander talking about geophysical monitoring of CO2 storage. And then there was also Andres Bush and Eric McKay from Harvard University discussing and sharing with us about the risk assessment in CO2 storage through coupled thermal hydrochemical mechanical processes. So if you have opportunity to attend this masterclass in the future, I would highly recommend it. One of the things I also found very beneficial was that I was able to meet with people from the industry, the host authorities, understanding their logic of doing CCS and why they impose some restrictions, and was also to meet other PhD students and gain insights from lessons learned of the existing projects. Okay, well, let's move on to MCDA GIS in CCS. Multi-criteria decision analysis is basically a structured way of decision-making method. It has been used to evaluate and compare multiple criteria for complex decision-making for so many years. I think it's been around since the 1960s. And also, what's good about MCDA is that it is a method where you could include both quantitative and qualitative criteria. So in CCS, that would be including technical, socioeconomic, and commercial criteria together. So MCDA GIS involves the integration of the MCDA method with the GIS software. So in the case of my PhD, I'm using QGIS for obvious reasons, because we want to reduce costs as much as possible for CCS projects. So for MCDA GIS data, the criteria or the problem that we're looking at are being structured spatially. Then the MCDA method is applied using GIS-based strategies. So in CCS, people commonly see criteria-driven assessment or suitability scoring. And this may or may not differ to MCDA, depending on the methods that are used. So you can see here an example of suitability scoring, which has been modified from version 2003. Essentially, what you see here is a list of 15 different criteria and a whole lot of numbers. So just to highlight a bit, MCDA GIS, it is about structuring problem or data spatially, then applying MCDA using GIS-based strategies. It is not translating scoring results into maps. So those are two different things. Okay. I'm going to give an example from offshore Norway. So here is a 3 criteria assessment for CO2 suitability in saline aquifer. So we have here top of aquifer, average aquifer porosity, and then we have a map of wells and fields. So these three maps are then converted using some GIS strategies into maps which reflect the criteria scoring. So for this example, I use criteria scoring based on the matrix developed by Eliis and Chadwick. So just on these three different maps, you can easily, the eye can easily catch the different scoring without really, reading anything. So that's why, looking at maps is much preferable. So the result of stacking these different criteria together, so adding up the scores, it creates a visually impactful suitability map. So on the right is the suitability map, and there are areas which we can immediately see that are more suitable for CCS, for carbon storage, and there are areas which are less suitable for carbon storage. Now, why MCDA GIS? Is because maps are impactful visual tools that support decision makers in making well-informed and comprehensive decisions. The process actually involves geological skills, which is understanding and interpreting maps. As a geologist, I think maps is my number one, is my look at data. So being able to just reflect and think about the criteria when I stack them together on a map makes more sense than putting in numbers on a table. This method is also widely used by the renewable energy industry, solar and wind in particular, for site suitability assessment, regardless of scale. So you would see studies being done at the country scale or at a more local scale. So in CCS, it would be regional, basin, or block scale. And there's also another possibility of data integration. So you can add in the GD map, you can have the proximity to source, proximity to facilities. There's also the possibility of including wind turbine locations, especially in the North Sea, where it's very busy. So endless integration of data, which can be included as part of your decision-making process. So for my PhD, the plan is, so right now I am reviewing literature for suitability criteria and applying GIS strategies on the criteria from technical, commercial, and socioeconomic aspects. And then I'll be developing a site suitability plugin using the MCDA GIS method. And then lastly, I'll work on a case study using the plugin. So that was a bit of an introduction to my PhD. I welcome if anyone has any feedback, comments, or suggestion towards the project, or even if you're interested in collaborating for a case study, that would be very much appreciated. Do drop me an email, which is there on the screen. All right, that's all. Thank you. Over to Eliis.
Thanks everyone for coming. As I had a nice introduction to start with, thank you very much. I won't go into that, but yes, I'm Alex Clarke. I work for Eliis. I've been here for about 5 months now, so not that long actually in the company, but I've been using Paleoscan for about 8 years now, so very familiar with the software And today I'll show you some nice applications of that software on the Smearhire fault storage, fault block for CO2 storage. If anyone in the audience has a better idea of how to properly pronounce that, then I'm all ears. And maybe we can catch up after this presentation for the drinks. This presentation today is a little bit of Frankenstein in the sense that it's not all just my work. A lot of it's coming from my colleagues Sven Fillet and Lucas Tortorolo in the Montpellier office of Eliis. So I've added a bit where I can to flesh out some of the introduction material and the conclusions, and also to demonstrate one or two of the new tools that we've got coming out in our upcoming release. Because we're paying for the beers after this, so you can sit through a minute or two of promotional material. So the talk itself, I'll go through an introduction to the Smearhire fault block, where exactly our study area is. I'll go through some of the structural evolution and where it's landed today as a result. We'll go through a history of the actual exploration there, how it started off with the hydrocarbon exploration and how that's moved through the various phases of CCS in more recent years. And then we'll present a lot of the work from our internal study within Eliis and come up with some conclusions. It's really going to be a very much, a very generic overview of the project. It's not, if you're an expert in this CCS project, it's probably not going to bring much to your attention that you didn't know before, but hopefully for a lot of you in the room, it will be a first introduction and a nice holistic overview of the project itself and some of the key challenges that are facing it. So we'll go on to the introduction then. Where are we? We are in the northern North Sea, the Norwegian North Sea. Smearhire is a north-south trending fault block located on the Horda platform. So you can see this regional structure map here in the lower right-hand side from the Norwegian Offshore Directorate. We are around this sort of yellow box is where this map is zoomed into. So we're approximately 75 kilometers northwest of Bergen and immediately east of the Troll oil and gas fields, which you can see on the map here. There's quite a bit of publicly available data in the area, and so we've got this 3D survey, this GN 1101, which I'll come on to in a bit more detail on the next slide. And alongside that, we've got a number of different wells and reports associated with each of those data sets. And the reason that we're bringing this up again now is because just over a month ago now, Equinor announced the results of 2 new wells on the area. So our 3244 well here, which actually penetrates the seismic data that we're using for this study, and the 3271 well a bit further to the south. So the seismic data sets, as I say, GN 1101, it was acquired in 2011 by GasNova. If you're not familiar with who GasNova are, they are the state enterprise in charge of CO2, promoting the CCS industry, essentially. So they acquired 450 kilometers squared back in 2011. It's a decent quality data set down to around the mid-Triassic, and beneath there, as we go into the acoustic basement, things get very choppy and very hard to see. But everything above that is of a really, it's quite well resolved. We can understand in good detail the various structures that we can see, and as you'll see later on in the presentation, there are quite a lot of attributes that we can derive from this data set and help us understand the depositional environment too. So not too limited in terms of the quality per se, but certainly a little bit limited in the lateral coverage of this data set, as you'll also see. So a couple of the major structures are nearly fully defined, but not quite on this data set. A couple of acknowledgements then, obviously to GasNova and Equinor for releasing the seismic data. Big thanks to them. And the use of all the wells data through this presentation material is thanks to the Norwegian Offshore Directorate as well. Very generous of them to publish it all, and a good idea in my opinion. So the structural setting of our fault block, as I say, we're a north-south trending fault block on the Horda platform in this sort of area. If we show a west to east trending diagram of the structural setting, it gives a really nice flavour for where exactly we are in our North Sea rift system. This map in the top, I should say, shows blue for Jurassic depot centres and purple for Permo-Triassic just in case you can't quite make that out on the screen there. And so we have our line going from the East Shetland platform on the left of our screen, right the way through our central Viking Graben and over into the Norwegian sector, up to essentially the Norwegian landmass on the right-hand side. And we're just in this area bounded by the yellow here. The Smearhire fault block is bound to the west by the Vette fault system, which is that one I just highlighted in pink. And to the east, it's bound by the EAGE fault systems, which I think the pronunciation there was quite good, but you'll have to tell me later if you know better, like I say. Each of these fault systems are westwards dipping basement involved fault systems, which were initiated during the Permian rifting of the North Sea. And that initial phase of rifting lasted until around the mid-Triassic. There was then a period of relative quiescence up until a second phase of rifting from the later Jurassic through to the early and mid-Cretaceous, depending on where exactly you are in the rift system. There was some reactivation of those faults, like I say, in that second phase, not as drastic as the initial phase. So if we take a little zoom in on the next slide of a seismic line on the Norwegian side of this of the Viking Graben, we can start to see the structure of the Smearhire fault block in a bit more detail. So this section goes. This is from the authors of Wu et al. 2021. It's a really good paper for getting an intro to the structure of the area if you're new to it, and I highly recommend it. I've got a few diagrams coming up on the next slides from them as well. And we can see that this seismic line that the section is modelled on runs from our Troll West oil field out in the far left side of this section, through a couple of gas accumulations within the Troll field, and then through this Vette fault system, which then separates the Troll area from our Smearhire fault block. And then to the right-hand side of that, we've got the EAGE fault system bounding that. I'm a little bit disappointed they don't have some kind of submarine mine out to the west of Troll getting some coal, because that would be a nice metaphor for our energy transition from coal through oil, gas, and then ultimately CCS on the right-hand side, but can't have everything. So I'm not too interested in the left-hand side of this section for now, so I'm going to hide that with our stratigraphic column. And I'm not going to dive into much of the actual depositional environments at this stage. We'll see that later on with some of the details we've got from our internal evaluation. But just to really highlight the thicknesses of these different units and how they change across the section and through time. So we've got in purple our Synrift section through to around the deposition of the Hegra, well, around the mid-Triassic. And you can see how the thickness changes across the Triassic respond to that Syn depositional faulting up until around this point here, where we start just getting infill of the available accommodation space. A key interval for today's talk is this yellow group. So this is the lower part of the Viking group, and it's really three different main reservoirs within that package. The Sonjefjord formation as the upper, the Fensfjord formation as the middle, and the Crossfjord formation as the lower. And each of those sort of interfingers with our header formation, which is a shadier unit. But in general, this yellow unit is really providing our reservoir target for both the initial hydrocarbon exploration on the license and the more recent CCS feasibility and activity. So that's a key unit for us to look at, and we can see that the thickness doesn't vary a huge amount across the area, even outboard to the Troll field. So this is the reservoir for all the Troll fields. We don't see a massive amount of thickness changes. That's because it was deposited in a fairly quiet time tectonically. The rift had started, or the second phase of the rift, I should say, had started further west during this deposition, but it didn't really start to affect our area until the later Jurassic and the early Cretaceous. So the later Jurassic deposition here is another key interval for us. It's our Draupner formation. This is a fairly chunky unit of just nice homogeneous shales, and this is our key cap rock, right, for every system that we're looking at, whether that's hydrocarbon or CCS, as I say. And again, we see some thickness variations, particularly into these faults, where we're starting to get reactivation of those big fault complexes as the rift is progressing eastwards. But thankfully, for our current projects on the go with CCS, they're still largely intact and fairly competent as seals go. So the lion's share of that second phase of rifting is really being felt by the overlying units in the early Cretaceous, so our Chromonol and Svart formation. Subsequent infill from various different Cretaceous units, and then up into our Paleogene with a really chunky base Nordlands unconformity over the area. So that's nicely evident right the way across our area. So that sort of sets up the structure of where we are today. You've probably noticed we've got these two structural closures, at least apparent on this line, one in the east and one in the west. And if we take a look at those in map view, we can see how those structural closures play out in sort of 2D. We've got those two structures are called alpha and beta, so alpha in the west and beta in the east. And there is also another structural closure within our Smearhire fault block further to the south. That's called the gamma structure. Unfortunately, that doesn't sit on our 3D data, and so I won't be talking about it today. But it is much sort of lower relief anyway, and less volumetrically significant anyway. So if we take a little look in 3D at these structures over our data set, we've got our top Sonnefjord horizon here in 3D. So north is sort of up to the top left of this image, and we can see our Øygarden fault system over to the right, and our Vetta fault system to the left of that image. Alpha sits in the crest of our sort of westerly point of the fault block. It's a three-way dip closure with fault trapping geometry in the footwall of that Vetta fault system, and it is intersected itself by a couple of northwest-southeast trending faults which came in from that second phase of rifting. There's been a huge amount of work to assess the fault seal risks with this project, and I'm not going to touch on much of that today. Suffice to say, the Vetta fault system is looking very low risk for its fault sealing capabilities, particularly because it's juxtaposed against a lot of the lower Cretaceous strata that provide a seal further west in the troll field. And these faults that cut through it from the sort of later phase of rifting are not thought to be that significant in terms of impeding the connectivity across them. There is a relay ramp to the south along this Vetta fault system, and this is key for both pressure communication across to the troll fields and also migration of fluids potentially outwards from the west to the east, as were initially believed in the early days of exploration, but more so, like I say, for pressure communication these days along the aquifers. And looking at the beta structure now, so this is over in the eastern margin of our fault block. It's a rollover anticline structure within the hanging wall of that Øygarden fault system. And there are really some more concerns around this structure compared to the alpha structure. And those concerns really arise from the fact that it is shallower, and thus the pressure system is less, the pressures are lower. Compound that with some of the pressure depletion that it will have felt from the troll production over the years. And there's a real risk that injecting CO2 into this structure, it might transform from our dense phase into our gaseous phase, which drastically reduces the actual storage capacity of that structure. There's also concerns over what exactly it's juxtaposing against within the basement. So it's juxtaposed against crystalline basement. We don't really fully understand the fracture networks within that basement and how far or how permeable those systems could ultimately be. And just to add a little sort of insult to injury, there's a crustal fault or two over the beta structure that does seem to cut through the overlying cap rock of that Strautner formation. So again, some fault seal analysis done on those overlying faults don't seem to be too much of a concern, but combined with the other factors that make it slightly less encouraging, it's definitely the lower ranked closure of the two. So if we go over the history of this block, it really started off, as you can imagine, with hydrocarbon exploration. The initial well on the Alpha structure was drilled in 1996 by Phillips. Incidentally, this was the same year that the Sleipner CO2 storage started. Not ludicrously far away from CCS at that time. But its primary target was the Sonnefjord formation, that main reservoir, as was producing at the time from the Troll fields to the west. And they were going for any number of stacked secondary targets, so upper, middle, lower Jurassic sands, Triassic sands, Paleozoic sands, if they could find them. So they TD'd down at just over 3 kilometers depth. They found some good reservoirs, as you might expect, in both the Sonnefjord formation and also in the lower Jurassic and upper Triassic, but no Paleozoic sands. I'd like to just implore anyone in the audience to take a note of how much better these final well reports look when you spend a little time doodling as a geoscientist on them. So if anyone could do artistic impressions of the maps and the dipping strata in future for wells, that would be fab. Onto the beta structure. This was drilled in 2008 by Talisman. It was the closest well to shore ever drilled on the Norwegian shelf. The landmass is just out of the picture here, really. Again, primary target of that Sonnefjord formation, and it also had secondary targets in the Brent group and the Statfjord formation. So less ambitious than the Alpha well, and it TD'd at just 1,300 meters, so a much shallower well. Interestingly, it took one pressure reading out the whole well and observed slight depletion in the Brent group. So again, this was 2008. There's been ongoing production since then. So that Troll production is really, it's making its presence felt a significant distance away. I've just made this little video on the right-hand side because you might be thinking, why did they drill beta if Alpha was dry? Using one of our new tools in PaleScan, you can model the migration pathways and change about with the sealing parameters of different faults. And there are indeed valid migration mechanisms to bring hydrocarbons from our Troll fields, spilling out from those structures, migrating eastwards up to just the beta structure and leaving the Alpha structure in a migration shadow. So it wasn't completely crazy of them. So we drilled 2 dry wells on the block. What next? You've drilled up the main structures, really. Well, as I say, and actually as I should have mentioned, the beta well was drilled in the same year that the Snøhvit CCS project kicked off as well. So CCS was definitely in, was being investigated in Norway at the time, and Gassnova were really trying to kick off more regional studies to encourage greater adoption. So they conducted a pre-feasibility study of the area from 2009 to 2012, and then basically commissioned a full-scale CCS feasibility report nationwide throughout the whole of Norway to assess the best areas for CCS projects. And Equinor were responsible for the analysis of the storage component there. So in this analysis published in 2016, they estimated that the Smeaheia fault block would be capable of receiving up to 1.3 million tons of CO2 per year for 25 years injected into the reservoir. And it ranked pretty highly due to its proximity to shore. Obviously, that's key. Proximity to existing infrastructure goes along with the proximity to shore. There's a lot of hydrocarbon infrastructure there, as well as CCS infrastructure, particularly as that's developing now. And the subsurface is reasonably well understood, so we can minimize and mitigate some of the subsurface risks there. So all of the data for Smeaheia was published in 2021 via CO2 data share. And that basically encouraged a whole raft of different studies from academia and industry alike. So one of those reasons that I think it's a good idea to publish this is that there's just an incredible amount of material available, looking at every different aspect of this block. So moving on from those initial feasibility studies, Equinor applied for and were awarded operatorship of the EXL 002 license, which is this blue license outlined here. The majority of that covers our Smeaheia fault block, and they were awarded that in April 2022. This license, as I say, is located in a very favourable area for CO2. It's pretty much a corridor. It's right next to the Northern Lights JV's acreage, which is a big joint venture between several of the super majors. And there's another license to the southwest of this that belongs to Aker BP. So it's a real sort of sweet spot for CCS in Norway. And there's a number of different pipelines running across the area as a result, which make the cost of the project, a lot more reasonable. It forms the storage solution for Equinor's CO2 highway Europe at the moment. It was initially studied to be part of the Northern Lights project, but I think they favoured that license to the west. And now it's just Equinor operated 100%. Pleasantly, there has been actually quite a lot of activity on it since. So PGS were contracted for acquisition of New 3D almost immediately after award to Equinor. So they started acquiring 4 months after the award of the license. And as I mentioned at the start of the presentation, they've actually recently drilled 2 new wells on that acreage. The primary driver of those wells was to evaluate storage suitability of the lower and middle Jurassic reservoirs, targeting each of those structures down dip. And the sort of news story, the press release from just over a month ago was that they look good, which is good. So both of the reservoirs are deemed to be suitable for injection and storage of carbon dioxide, but obviously there's a whole suite of data that is yet to be released, and they will be diligently planning through at the moment to address some of the other subsurface risks. So taking a look at the study that Eliis have done then. Before I dive into this, just for those of you who aren't familiar with PaleScan as a software, I'm going to go over the sort of method and how it differs to a lot of classic interpretation software. If you've already seen this kind of presentation before, I've put up a little slideshow of the what's the name of the pub that we're going to? Anglesey Arms. There we go, in the bottom right. So you can just think of that while I'm presenting this. So PaleScan itself is quite different to classic interpretation software in that we don't pick horizons one at a time through inline crossline interpretation or do just 3D auto tracking one at a time. We actually create a full relative geological time model for the entirety of our subsurface data set. I won't go into details now as to how you do this, but essentially you end up with this model which has relative geological age values appended to it from oldest at the base to youngest at the top, and it fully defines the structure in 3D and is stratigraphically organized, right? So a whole load of things that we can do with this once we've got it in place, and you sort of front load the workflow by generating this, but it's really beneficial in the long run. This is a discrete color bar, by the way. It's not actually that, it's more like a continuous color bar because they get vertically very fine increments. But we just use this color bar to really define the structure. Whilst I've got a captive audience, and it's not often that I have a captive audience, I wanted to basically iterate this point because I think historically in the UK, we've not been amazing with our uptake of PaleScan. And like I say, I've been working with this software for close to a decade before actually starting to work for Eliis. And I thought that it was more widely understood than it is, I think. So we generate this model grid as the interim step between our seismic and our relative geological time model. And PaleScan does an automatic interpretation based on that, which we then should spend some manual interpretation time improving the interpretations that PaleScan has done automatically. Unfortunately, a lot of people just take the automatic interpretation straight through to a relative geological time model, and you end up with something that looks a bit like this. So you'll do well in the overburden and in the less structurally complex areas, but in areas where it's complex or poorer data quality, you might end up with something that looks like this. And at that stage, some people will say, okay, PaleScan isn't working here, let's go back to Patrol, right? That's not the case. You just need to spend some time doing the manual interpretation. And so we can go in, and because you can see here it's making incorrect assumptions across the fault. PaleScan's already picked every single part of the horizon throughout the whole volume, so it's as quick as saying this is the same age as this, same age as this, and doing that a couple of times for different horizons. And you can see how much better your resultant RGT model is. So while some people will generate an RGT model that looks like this from their automatic interpretation, if you spend a few, even just a couple of hours doing your manual QC of that automatic interpretation, the resultant RGT model is just night and day. So that's my little plug to say, spend a bit of time on the manual interpretation. If you've seen Paleoscan before 10 years ago, do get in touch. I'm sure I can show you some things that would surprise you. So on to our model for the Smearhire fault block. Here's just the seismic data that we've got. I think this is the seismic relief attribute. The geomodel that we created for the fault block really concentrated obviously on our middle Triassic and upper. We weren't too concerned with the basement, so didn't spend much time there. Likewise with the very much the overburden. Once we've generated that RGT model, we can generate horizons from the top to the base of wherever we've got a competent RGT model. And so this is just an illustration. We can, if we wanted, extract 10,000 horizons between the top and the base. So we can get infinitely fine vertical increments, stratally slicing our seismic along reflectors that it should be seismic conformant wherever it is. So we generated an absolute age model as well for this fault block, and we'd also generated a velocity model using the same principles. So taking our average velocities from the wells, propagating those out through the relative geological time model to give this nice sort of fairly layer cake approach to velocity modeling. It's not just conversion into the depth domain that we can do. Because we have our relative geological time model available to us, we can perform a transform into the Wheeler domain. So here we are going from our two-way time into our Wheeler domain. And you can see, if you're familiar with the Wheeler domain, it essentially flattens out our relative geological ages across the section. So our z-axis is, or y-axis is geological time as opposed to two-way time. And it introduces these gaps where we've got our key convergence of relative geological ages. And this represents to us the areas where we've got non-deposition or erosion, or just really condensed sequences. So it's a fantastic way to look at the seismic data and putting this in context of the structural evolution story that I presented earlier. We can make several assertions about the various gaps that we're seeing on the seismic. So if we post on our key surfaces for the interval of interest, we can see that we've got this area of Triassic non-deposition, and this is probably likely due to we've got fairly even deposition of our Triassic sequence earlier on, and that's when it's evolving with the sedimentary deposition of our faulting. But as that impact of the rifting fades towards the later part of our Triassic, there's not enough accommodation space in our basin to keep the sediment depositing uniformly. So we see a progradational sequence out there and some erosion of the hinterland potentially, or just a condensed sequence. Further up, we can see on the west part of our fault block, we get this fairly chunky erosion from our rebound of the fault block from the Upper Jurassic to Lower Cretaceous rift phase. And that's where we see some erosion of our Draupner formation overlying the alpha structure. So this may be a bit of a concern. It does thin the Draupner formation over our alpha structure, but not too drastically, luckily. And we also see this little smidgen over here, which is a really nice representation of the timing of the faulting, the rollover anticline formation of our beta structure. And so we can see that occurred slightly earlier than the sort of rebound and full erosion over our Veta fault system. And then coming in through all of that, we've got that base Norderland unconformity, which just wipes out a lot of the section, thankfully leaves our beta structure untouched. So a nice little transform that we can do there within Paleoscan to our Wheeler domain, and yes, some notes on the evolution there as a result. This is all in 3D as well, so to understand the seismic stacking pattern, it's a great place to play about with that and get to grips with how these unconformities are playing about. We picked various different faults across the area. Obviously, faults are critical in our case study. I'm not going to go through this because we're getting a bit further on in time. this is some of the meat of what the folks in headquarters had done. So looking at all of these various different stratal slices from our mid-Triassic section up towards our sort of Droutner formation, and seeing any hints of depositional systems that haven't necessarily been picked up in the literature as much. So we're looking down in the Hegel group. So this is in the Triassic to start with. You can see this column on the left-hand side. So we're in the Triassic. These have been observed before, these sort of channel systems, as part of our alluvial deposition, and basically there's a bit of a progradation of this system from eroding from our footwall and pushing out westwards into the basin. So we see a number of different intervals with channel systems, and when we flatten on the top of the Brent group here, we can see these sort of shallow cliniforms prograding as we push more into the lower Jurassic and evolve into a bit more of a deltaic system. Once we're in the Brent group, we see some nice indications of actual dendritic drainage systems from our plateaus that have been popped up slightly into our sort of meandering channel systems just outboard. So we see, I was a bit skeptical initially when I saw this, but there's some good examples in the literature as well of these broader sort of meandering channel belts from our popped up plateaus around in this time. If anyone's got any opinions about what these little features are, I would be interested to talk after the presentation as well. They look like this in cross section, which looks quite channel-esque, a bit erosional, possibly pockmarks. Yeah, bit of a mystery to me, so happy to have a chat afterwards if anyone's studied these before. Moving up into our key intervals for reservoir now, our Viking group. This had really moved to a shallow marine environment by the time we get there, and you can see a number of different intervals with various cliniforms and tidal bars and things like that. I would say it's a bit disappointing, given the quality of the data set, how few features there are actually within this data set. So I'd really like to see some of the more recent data that's been acquired over here. Equinor acquired that seismic, as I mentioned, in 2022. I bet there's some stunning features on that data, but we'll do the best we can with this data anyway. So merging our sweetness and gamma ray property models from our well logs, we can see some correlations of these sweetness maps responding to better sands. And so we can see some sort of variation laterally there as well. So mapping out some of these key geobodies in our 3D view, you can see how that system has basically evolved from our Triassic continental system and prograded outwards in a broad sense through to our shallow marine systems of the early Jurassic, and then subsequent transgression laid down that really nice and thick Droutner formation seal over the top. Deep marine shales. We do get some of these faults cutting through, as you can see, but a lot of fault seal analysis done on these, looking at the prevailing stress orientations and current stresses on the subsurface, and it's not thought to be a huge risk in this area. So just a bit of a discussion about some of these features, getting some analogs from what we can see in these attribute maps versus analogs that we can see today on land. We've got some braided channelized systems from our Triassic into some alluvial fans of a similar nature. Higher up in the section, we've got that dendritic drainage with meandering channels on our sort of floodplain environment, and then up into our more shallow marine sandbar dominated environment. And if we stick on the general periods, we're going from our sort of Triassic systems here, our continental Triassic systems, through into our Jurassic and our Cretaceous and depositional environment there. Some of the supporting literature published by Wurtzen et al. In 23 spots, like I say, some of these features as well, and is a really nice confirmation of the depositional environments in a broader area of seismic that's available. So the well encountered, because this was drilled just down dip of the 3144 well was drilled just down dip of the alpha structure, and obviously now having been through all these depositional systems, it's we were sort of wondering what it would encounter. Its primary purpose was to explore the nature and quality of the reservoirs within that Viking group. So if we take these bullet points one by one from Equinor's press release, it encountered the Draupner Formation with 142 meters of homogeneous shale. That is a win. That is a competent shale unit as a CAP. That's good. The Sogne Fjord Formation, the main good quality reservoir, really 106 meters of sandstone with good to very good reservoir quality. So that's another good win. Just up dip in the 1996 well, it was 86 meters, I believe, or 68 meters, one or the other. That might be due to a difference in the interpretation of where the markers are, but still good result. Deeper down, the Fensfjord and Crossfjord came in with good reservoir quality as well, not quite as good as the Sogne Fjord. And then we've got another sealing unit in the Drake Formation beneath these, which caps the Cook and Johansson formations, which are secondary targets really for the injection of the CO2. So again, good thicknesses of that homogeneous shale and a decent thickness of the reservoir too. All we can really go by at this stage, obviously, is what Equinor have decided to release publicly. I'm optimistic that in the long run they will release some of this data fairly sharpish. But some of the other points that were mentioned in this press result were that formation pressures had been taken for both of those new wells. And they do show depletion in those Cook and Johansson formations. So these are within the Dunlin group, or just at the base of the Dunlin group down here. And that depletion increases as you move upwards in the section. So that is, a fairly poor, I mean, it was expected, but it's not desired for the CCS injection, because that, the lower the pressure you're injecting the CO2 at, the more space it's going to take up with less injected from the surface. It did say they conducted injection tests, and those were the results of those were positive, so it's viable as an injection reservoir. And that data is now going to be analysed in greater detail, obviously, and will inform the basis for the FID decision that is yet to come. So that's going to be the critical decision point for Equinor. I would imagine at least several months of analysing these well data to establish if this will make a viable project. I'm going to show quickly now some of the tools that we've used in PaleScan for going through these various formations. This is a gamma ray volume that we've created by propagating out our well logs into the relative geological time model. And because we can pick at really fine increments from our relative geological time model, we can create many more surfaces and sort of do a well-based interpretation really, and extrapolate that out to seismic, compared to if we were just dealing with the resolution of our seismic trace, for example. So what we can do here is really get into much more granular detail about separating out the intraformational seals within these reservoir units, and try and make an interpretation as to the vertical connectivity of these different facies. And what we can do is we can take each of those different surfaces into our new CCS module, which is being released in next week's release. So this is a new module, like I say, in PaleScan, which essentially analyzes the structure of a horizon. We can play about with loads of different parameters in here, and we can model how the migration pathway of our CO2 would behave given certain conditions. So here we're just specifying a base horizon, so we're not taking a full an unlimited package. We're going to pop in an injection location, and I've just chosen an injection location on that relay ramp to the south of our data here. And we can see now these various accumulations that are sort of modeled on this depth structure surface here. So if I can use this scroll bar at the base of the map to take it sort of step by step through that migration of our fluids, and you can see how these different accumulations gradually fill to spill and then move onwards and outwards and fill up other structures on the horizon. So at the moment, we're basically assuming all of these faults seal and have no sealing sealing issues in terms of integrity. We can also choose to include then a max column height for either capillarity or for just full breakdown of seal. So if we choose to introduce a maximum column height for capillary pressure reasons, then we can see how our accumulations respond to that. And again, play this back through time and forward through time. And you can constantly see as we're moving this time through the migration simulation, you can see the net volume of each accumulation changing. So it's a really nice quick way of screening through various different scenarios for our CO2 storage. And so what I do here is come in to take a closer look at how some of these faults are behaving, because obviously there's a lot of debate in the literature about which of these fault systems are sealing and which aren't. And so we can play about interactively with whether we want to extend these faults to be fully connected, as I'm doing here. And if so, once those faults are connected and fully inhibiting the flow of CO2, how our injection pathways might differ. So I'm just removing those from the view, and then we can put in some injection again, play about with that. And you can see again, if we've actually chosen to seal these faults now, then we get a completely barren alpha structure. For the CCS project in question, we're actually looking at injecting from that more recent well, which lies in a bit of a saddle for us. So I can show that later, the results of that. But if we can play about, like I say, with the sealing properties of these faults and add in potential leak points as well, if we want to. There's a lot more to this tool, and I'm sure you'll see a webinar or something coming up in future, but just to make you aware of this, it's a great tool to interactively play about with different scenarios. The gross rock volume estimate from the chaps in Montpellier before this tool was available, they had to go through a number of sort of more traditional workflows to generate the geobodies and assess the GRV. Here are the assumptions that they've made for that. I'll just skip through these fairly quickly because we're nearing time now. This was their sort of manual attempt at looking how the fluid would migrate, and their assessment of the vertical separation of these key units. In a more pessimistic estimate of the GRV, they were coming out with a GRV of around 100 meter column height, which gave the GRVs that you can see on the right hand side, and you can see that sort of witch's hat up into the fault zone. And with a more optimistic scenario, in scenario 2 of a 200 meter high CO2 column, there's obviously much greater volumes that you're able to store, given the lack of that pinch out up dip. In a broad sense, our volumes from that GRV calculation agree with the volumes that have been published in that 2016 feasibility study from Statoil, which is always nice to see. But you can see here the extent of the alpha structure off of that 3D coverage, and the beta structure is really primarily limited to our 3D. So finally, onto the summary. This is, an actively maturing CCS project. It's not something that's just all words. There is, a lot of money being put into this project. The alpha structure is looking fairly encouraging as far as the data to date shows. The beta structure is fairly challenged because of the pressure depletion story and the uncertainty over the fault seal, both in the overburden and also laterally into the basement. And the depositional environments have been characterized with the help of these RGT slices in the work we've done in Paleoscan. FID is the sort of next and could argue final hurdle for the project, which we'll be keeping a close eye out for in the coming months and next couple of years, I'd imagine, really. In terms of future work to do in Paleoscan and on this project, I think I'd be advocating for creating multiple different GRV assessments using that tool to simplify it. This is something I've only had access to for about 5 days now, so this was performed in a hurry. I'm also going to be keeping an eye out for this 3144 data to see if that's published and to see if we can integrate that to get a better understanding on how we can correlate those intraformational seals between the two wells on our data, and use that to additionally steer those GRB assessments based on the vertical connectivity of the units. So with that, I will thank you all for your attention. Hopefully you found that somewhat interesting, and we can open that up for any questions online or in the room. Thank you very much.